All right, so for this lesson, we're going to be able to get into some actual probability rules and some probability models. So a little bit of vocab. We have what's called a sample space, and that is the set of all possible outcomes. The sum of the probabilities of all the outcomes in your sample space have to add to 1. So if I'm flipping a coin, my sample space is heads or tails. So 50% chance it'll be heads, 50% chance it'll be tails. Add those up, that's a 1. If I'm going to roll a dice, then my sample space is, I could roll a 1, 2, 3, 4, 5, 6. Probability of each one is 1/6. Add all those up, I get a 1. Probability model is a description of a chance process that has 2 parts. First part, you have to have your sample space. The second part, you're going to state the probability for every item in your sample space, just like I just walked through. So let's look at another example. A sample space S can be very simple, the 2 examples I gave you, or very complex. If we toss a coin once, there are only 2 possible outcomes, heads or tails. All right, let's look at this one. Human eye color is controlled by a single pair of genes, one from the father and one from the mother, called a genotype. Brown eye color, B, is dominant over blue gene L. Therefore, in the genotype BL, consisting of one brown gene and one blue gene, the brown gene dominates. So a person with BL genotype is going to have brown eyes. If both parents have brown eyes and both parents have genotype BL, what's the probability that their child will have blue eyes? What's the probability that they'll have brown eyes? All right, so let's start defining our sample space. So those of you who have taken biology have a leg up on this. Let's see, because this isn't a live class, I don't get to ask you guys, but this is some sort of square, like a Punnett square or some sort of square. It's got a name to it, and I'm sure you guys are all saying it, but I don't teach biology, I don't know it. But this is where you guys would tell me what it is. So here we go, we got the mom and we got the dad. Now, the mom and the dad both have brown eyes, but their brown eyes came from their genotype BL. So there's their genotype, and there's dad's genotype. Okay? All possible outcomes are all possible combinations of these genotypes. So the kid could have BB, BL, BL, or LL. So let's start by defining the sample space. My sample space is BB, BL, BL, and LL. What's the probability that the kid's going to have blue eyes? Well, B is dominant. So if B is in the genotype, that kid's going to have brown eyes. So the only way this kid's going to have blue eyes is right here. So here's how you write it. The probability of blue eyes, or you could have written the probability of LL. I like the blue eyes better because it's more user-friendly, is 1/4 or 25% if you wanted to write it that way. Then it wants to know the probability that I could have brown, or this kid could have brown eyes. And that's 3/4. Because all 3 of those outcomes, 3 out of the 4 outcomes, will result in brown eyes. Ta-da. Ms. Patterson is making up a final exam for a course in AP Statistics. She wants the last 3 questions to be true or false. To guarantee that the answers do not follow her favorite pattern, she lists all possible true-false combinations for the 3 questions on slips of paper and then picks one at random from a hat. What is the sample space? A huge common misconception here is that the sample space is true and false. That's not true. That is false. The sample space are the results for the 3 questions. So, and I have to do this systematically. You come up with your own system for how to do this. It has to make sense to you, but I wouldn't randomly write answers down because you're going to lose track of where everything has been. So I'm going to start with trues. So that could be the answers for the last 3 questions. Okay, now I'm going to enter one false answer. I'm going to start on the back, move them to the middle, and then move them to the front. So I have 0 false answers, and then there's 1 false answer, and all the possible combinations of having 1 false answer. Now I'm going to do 2 false answers. 2 in the back, 1 in the front, 1 in the back, 2 in the front. Okay, so I've done 0 false, 1 false, 2 false. The last one is all 3 false. So here is your sample space. So again, the sample space is not true false. There are 3 questions. What are the possible outcomes for those 3 questions? So the sample space has a total of 8 outcomes. So what's the probability that all 3 of them are true? Well, it's 1/8, 1 out of the 8. You guys get 3 trues in a row and everybody panics because you think the teacher's messing with you. That's not true. We don't do that, by the way. Or if you're doing multiple choice and you get 3 C's in a row, you think something's wrong. God forbid you get 4 C's in a row, then something's really wrong. But we don't, well, I don't ever look at the order of the answers. Okay, gonna roll the dice. Many board games involve rolling dice. Imagine rolling 2 fair 6-sided dice. We've got one that's red and one that's green. So these 2 dice are distinguishable from each other. Give a probability model for this chance process. So the picture that you see is its sample space. So we'll say that the dark one is red and the lighter one is green. So if I look at the first column, they left the green as a 1 and then did all possible combinations of the red. Then they flipped the green to 2 and did all possible combinations of the red. So he's red, he's green. Okay, and the green was at 1. Now the green's at 2, and they ran through all possible combinations of the red. So there's a systematic way to do this. So there is your sample space. Okay, so it says give a probability model. Okay, so probability model has 2 things. It has the sample space, and it has the probability for each item in the sample space. So S for my sample space, there he is. Okay, the probability of each outcome, well, each outcome, and this is an outcome, and that's an outcome, and that's an outcome, all have an equal chance of happening. So the probability of each outcome, 1, 2, 3, 4, 5, 6, 36 is 1 out of 36. Now, saying that we had 2 different colored dice helped with the, let's see, let's look at this guy. This 4, 1, and that's 1, 4. So rolling two different colored dice, 4-1 and 1-4, it's very easy to see that those are two different outcomes. Everybody see that? But then notice 2-2, there's no other 2-2 on this board because the green is 2 and the red is 2. So the green is 2 and the red is 2. So I can't have that another way. So he's only on here one time. And doing it the systematic way really helps see that. Same thing with 6-6. All of these, all of your diagonals only happen once. But 4-1 and 1-4 can happen two different ways. 4 with the red and 1 with the green, or 1 with the red and 4 with the green. A probability model does more than just assign probability to each outcome. It allows us to find the probability of a collection of outcomes, which we will call an event. Okay, so we have outcomes and we have events. An event is a collection of outcomes from some chance process. An event is a subset of the sample space. Events are usually designated by capital letters like A, B, C. If A is any event, we write its probability as P of A. P stands for probability. So P of A, the probability of event A, equals the number of favorable outcomes over the total number of outcomes. Okay, now let's make sure we understand what an event is. So let's look at the next example. In the dice rolling example, let's define event A as the sum is 5. What is the probability of A? Okay, I'm going to go back to my dice. So the sum is 5 is my event. Let's just start with a clean slate. So that could happen here, 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 or here. Those are all the possible outcomes. Notice that it's more than one outcome. So it is an event. An event is a collection of outcomes. Now, they all produce the favorable outcome, which is the sum is 5. So when I go back here, I'm going to write the probability of A, and they have already defined event A. I can't just use a letter that I haven't defined. So if it's not defined for you, you would have to go over here and write this. A equals sum of 5, or sum is 5, whatever. So the probability of event A happening is the number of favorable outcomes. Well, it could happen 4 different ways. So that is the number of favorable outcomes over the total number of outcomes. Well, we already said there were 36 in the sample space. And then we would reduce that. So the probability of getting a sum is 5 is 1/9. And you could turn that into a decimal if you wanted to. Okay, now define event B as the sum is not 5. What is the probability of B? Okay, well, if 4 of them will give me 5, then 32 of them won't give me 5. And then we can reduce that by 4. Now, notice something. Probability of A plus the probability of B equals what? 1. Because those two probabilities, those two events, use every single outcome in the sample space. And as we discussed earlier, every outcome in the sample space's probability has to add to 1. And you can look at it as 32 over 6 plus 4 over 36, or 1/9 plus 8/9. The probability is 1 because these two particular events use everybody one time in the sample space. If you roll a die, what's the probability that you'll roll a 5? Okay, here's how we're going to write it. Probability roll 5. Okay, probability that I'm going to roll a 5. Well, I have a die. It has 6 sides. There is 1 5 on there, so the probability would be 1/6. So favorable outcomes over total outcomes. My sample space would be 1 through 6, and the only one that's favorable would be the 5. If you roll a dice, what's the probability that you'll roll an even number? Okay, here I go. Probability, even number. Now, you could over here say A equals roll even number, and then go probability of A equals. You could do it that way, or you can do it this way. Either way is fine. The point is you are communicating what you are finding. So an even number, well, I've got 1 through 6 in my sample space. 2, 4, and 6 are even. That's 3 favorable outcomes over 6 total outcomes, and that's a 1/2. If you roll a die, what's the probability that you'll roll a number less than 5? Less than 5. You could have done probability number less than 5. You could not use an X because you have not defined what X is. But I can use words. So I can say a number is less than 5. Probability that a number is less than 5. Well, I've got 1 through 6. 1, 2, 3, and 4 are all less than 5. So that probability is 4/6, which reduces to 2/3. Again, you could turn these into decimals if you wanted to. If it's multiple choice and they go decimals, you go decimals. If they say fraction, you say fraction. Ms. Patterson is making up a final exam for a course in AP Statistics. She wants the last 3 questions to be true or false to guarantee that the answers do not follow her favorite pattern. She lists all possible true-false combinations for the 3 questions on slips of paper and picks one at random from a hat. Should sound familiar. List all possible outcomes of the last 3 questions. Boom, we already did it. That was 2 slides ago. What is the probability that all 3 items will be false? Okay, so I'm defining an event. I have 8 items in my sample space, and I'm going to define this event. Let's say event A, and you could do FFF, or you could say all 3 Fs, and then you can do the probability of A. Or you can not do this and just write the probability of FFF. Either way, as long as you are communicating what you are finding. Do not expect the grader, me, or an AP grader, to know what it is you're thinking. You have to communicate that. Don't assume anything. There's this beautiful sign at the front of my room that says nobody is less impressed with how much you think you know than an AP grader evaluating how much you actually know. It's not about what's in your head. It's about what you put on that paper. Okay, so probability that all 3 items will be false. Well, there is 1 favorable outcome out of the 6 total. Oh, no, sorry, there aren't 6 total. So sorry. 8. What is the probability that exactly 2 will be true? Okay, we'll define event B, 2 T's. Probability of event B, let's see, 2 trues. 1, 2, 3. 3 out of 8. Nice. Okay, so I hope you know sample space. I hope you know what a probability model must show. I hope you know what an event is and how to find the probability of an item in your sample space and how to find the probability of an event, which is multiple items in your sample space. Okay, so now we're going to talk about the not. The probability of not A is the probability of the event not happening. It is called the complement of an event. So the probability of not A is 1 minus the probability of A. So if there's a 1 in 9 chance that all 3 multiple choice answers could be true, then there's an 8 in 9 chance that they won't all be true. You will also see this, let's see, probability, complement, probability, looks like C is an exponent. It's just this notation. Probability C of A means the complement of A. That means the probability of not A, which means 1 minus the probability of A. The probability that a college student without a flu shot will get the flu is 45%. What is the probability that a college student will not get the flu if the student had not had the flu shot? Okay, the probability if I don't have a flu shot, but I do get the flu is 45%. The probability that I have not had the flu shot and I will not get the flu is the not of the I will get the flu. Okay, let's write this out. The probability that I get the flu is 0.45. So the probability that I don't get the flu is 0.55. So what you're doing for this is the complement that I do get the flu. That's the not part of it. So this and this problem are saying the same thing. And what we did was that. And you have to show where these numbers are coming from. You can't just pull a 0.55 out your butt. You have to communicate where it came from. You have to show them the statistical notation, which means you have to do it for me too. A veterinarian tells you that if you breed 2 cream-colored guinea pigs, the probability that an offspring will be pure white is 25%. What's the probability that it won't be pure white? Okay, now let's practice this. Let's practice what we're preaching. I am going to write first what I have. I have the probability that it will be pure white, and that is 0.25. That's me translating what I was given. So that's a 0.25. I want the probability that it won't. So I want the complement of that. Now, when you're doing this and you're checking your homework, I don't want you to just go find the 0.75 and say, ooh, I got it right. Because odds are you're going to do that in your head. But if you give that to me on an FRQ and this thing is worth 3 points, you've lost 2 of them. You get 1 point for having a right answer because you have the 0.75. You have to be able to write the stats. So you have to be able to write P of C, of the pure white, is 1 minus the 0.25, and that's where the 0.75 comes from. So focus on that part. All right, some rules of probability. The probability of any event is always going to be between 0 and 1. So the probability of A being the event, is always going to be between 0 and 1. Could be 0, could be 1. Could never happen, could be guaranteed to happen, but it will never be negative, and it will never be bigger than a 1. All possible outcomes together must have a probability that add up to 1. All right, now this says P of S. Okay, remember what S stands for. S stands for your sample space. So the probability of everybody in your sample space must add to 1. If all the outcomes in the sample space are equally likely, and that's not always true, but for right now it is, the probability that any event that you define as A occurs is the probability of A equals the number of favorable outcomes over the total number of outcomes. Think back to the dice. Probability that the sum adds up to 5 over the total number of outcomes. Well, that could happen 4 different ways out of 36 possible rolls. The probability that an event does not occur is 1 minus the probability that the event does occur. All right, and there you can see it again. Now they put the C on the event this time. So probability of a complement is 1 minus the probability of A. If two events have no outcomes in common, the probability that one or the other occurs is the sum of their individual probabilities. The probability of A or B is the probability of A plus the probability of B. Now here's the kicker, and this won't always be the case, and once we get here, this really causes some people some issues. So let's lay a solid foundation right here. The kicker is no outcomes in common. So if I were to say, what's the probability that you're going to get an A in AP Stats or that you're going to get an A in Honors English? Well, do those two events have outcomes in common? Could you get an A in AP Stats and an A in your English class? Absolutely. Then this formula does not work. You cannot take the probability that you're going to get an A in Stats and add to it the probability that you're going to get an A in English, because they have outcomes in common. You've got kids that get A's in both, and because of that, they get counted twice. And we adjust for that later. So right now, this only works if the two outcomes have nothing in common. So an example, the probability that a Math 1 student gets an A, and event B is going to be the probability that a pre-cal student gets an A. Well, those two outcomes have nothing in common. You can't be in Math 1 and pre-cal at the same time. So I can take the probability that a kid's going to get an A in Math 1, and I can take the probability that a kid's going to get an A in pre-cal, and I can add them together. I cannot do the probability that you're going to get an A in AP Stats and or the probability that you're going to get an A in pre-cal, because I have kids in pre-cal and AP Stats. So there is overlappage, which means I cannot treat that to this formula. It only works when the two events have nothing in common. Now there's a word for that. It's called mutually exclusive, and I have also seen them refer to it as disjoint. Mutually exclusive. Two events are mutually exclusive if they have no outcomes in common. and so they can never happen together. Okay, now look at this. I want you to focus on the words here. Here's an or and here's an and. They mean two crazy different things in probability. This is event A or B. This is event A and B. If the probability of A and B happening together is 0, then we are mutually exclusive, then we can use that formula. The probability that a Math 1 kid gets an A and the probability that a pre-cal kid gets an A is a 0, because nobody can be in both those classes. Which means I can use that formula up there. But if there is overlappage between the two events, then they are not mutually exclusive, because the probability of A and B is not 0, because A and B can happen together. Okay? If you need to, pause it, rewind, and just listen to that from the number 5 down. Listen to that one more time and digest that. Okay, below is a two-way table that describes the responses of 50 subjects to a survey in which they were asked, do you watch TV for more than 30 minutes a day? And then they were also asked, what kind of pet do you have? Okay, so I have two variables here. I have watch TV for more than 30 minutes a day. My responses are yes or no. What type of pet you have? It was either a cat, a dog, or a bird. If one person from this sample is randomly selected, list 2 mutually exclusive events for this chance process. Mutually exclusive means they cannot happen together. Well, if I ask a person, how much do you watch more than 30 minutes of TV? Then they cannot say yes and no to that question. It is one or the other. Those two events are mutually exclusive. So I'm going to say event A is going to be watch more than 30 minutes TV. And event B is not watch more than 30 minutes of TV. Okay. What kind of pet do you own? Well, can someone say that they own a cat and that they watch more than 30 minutes of TV? Yeah, there are 10 of them. So owning a cat and watching more than 30 minutes of TV are not two mutually exclusive events. Now, having said that, look at your numbers. What's another pair of events that are mutually exclusive? Right there. Nobody had a bird and didn't watch more than 30 minutes of TV. So there are 2 events that are mutually exclusive. Event A, I own a bird. Oh, no, I don't own a bird. Sorry, that's a no. I don't own a bird. No, I do own a bird. Yeah, sorry. 4 people own a bird, and all 4 of them watch more than 30 minutes of TV. Okay, so let's do this again. All right, so 2 events that are mutually exclusive. Number 1, event A, I own a bird. Event B, I do not watch more than 30 minutes of TV. Those are 2 events that do not overlap. There is nobody who owns a bird and watches more than 30 minutes of TV. So the probability of A and B is 0. Boom, it's right there. Okay. Distance learning. Distance learning courses are rapidly gaining popularity among college students. Randomly select an undergraduate student who is taking a distance learning course for credit and record the student's age. Sorry. Here is the probability model. Okay. Taking and record their age. Here's the probability model. Okay, so I have age groups. So my sample space, so here's some terminology. Here's a probability model. So here's a model in the flesh. I've got the age group in years. And then I've got their probability. So I have 1, 2, 3, 4 items in my sample space. I have all of their probabilities. All of those probabilities individually are between a 0 and a 1. And if I add them all up, they all equal 1. And I just did A. Show that it is a legitimate probability model. So for part A, you would write the probability of each outcome is between a 0 and 1. So individually, they are all legit probabilities. The other thing that has to happen is the sum of all the individual probabilities must equal 1. Okay, B. Find the probability that the chosen student is not in the traditional college age group, which is 18 to 23. Find the probability that the chosen student is not in the traditional college age group. Okay, so I'm going to define event A. Now, this is a not, so I can do this 2 different ways, and I'm going to show you both. I can say that event A is not in 18 to 23 year group, and then I can find the probability of A. Okay, or I can let A be in the 18 to 23 year group, and I'm going to find the probability of A complement. So do you guys see there are 2 ways to write this, and they are both legit, and they both communicate to the grader or the reader the same information. Both of them are finding who is not your typical college age kid. So if I do this one, not in 18 to 23, okay, so that means I need to do the probability of 24 to 29 plus the probability of 30 to 39 plus the probability of 40 plus, which is 0.17 plus 0.14 plus 0.12 to 633, 43, dang it, 0.43. Okay, so there's one way, and that's everything you have to show, no exceptions. All right, if I do it the other way. So the other way is, all right, take who's in A and do 1 minus it. So formula first. So 1 minus the 18 to 23 is 1 minus 0.57, which is 0.43. Now, I'm not going to ask you which way was simpler. You do it whichever way it makes sense to your brain. Just remember, if it's multiple choice, the answers could be the setups. So just make sure you're comfortable with both. But you can choose which one you want to write. But guys, notice, I did not just slap down a 0.43. You can't do that. It's right, but you're going to lose points because you're not showing where the information came from. Now, if this was multiple choice, absolutely. You don't have to write a thing. But if this is an FRQ, you have to define event A, and you have to show me where that 43 is coming from. Okay? All right, check your understanding. Choose an adult at random. Define 2 events. Event A, the person has a cholesterol level of 240 milligrams per deciliter of blood or above, which means they have high cholesterol. Event B, the person has a cholesterol level of 200 to 239, which is borderline high cholesterol. Okay, let's take a second. Let's process that information. I haven't read a thing about what they're asking yet. Let's process that. What can you tell me about event A and event B? They are mutually exclusive. You cannot have someone who is in group A and who is also in group B. It cannot happen. You have one cholesterol level. You get one number. So it can't be in both groups. So these two events are mutually exclusive. According to the American Heart Association, okay, now they're giving me the probabilities. The probability of A, which is totally fine because we have defined that event, is 0.16. That means 16% of all adult Americans have a 16% chance of being in the high cholesterol group. And probability of event B is 29%. Explain why events A and B are mutually exclusive. Okay, we've kind of already talked about this. So I want you to pause it, take a second, write a sentence. Okay, so I have, because your cholesterol level can't be 240 or above, and then also be between 200 and 239. The two events cannot happen together. Say in plain language what event A or B is. Then it wants us to find the probability of A or B. Okay. Let's see, plain language, event A or B. Not the probability of it, just the event. So event A or B, the adult's cholesterol level is either 240 or above, or, there's your keyword, it is between 200 and 239. And if this was a test or the AP exam, I would include my units of measurements, which is milligrams, I think, per deciliter. Yeah, milligrams per deciliter. What is the probability of A or B? Okay. So the probability of event A or B, there they are, is going to be, now you can't just poof, you can't poop out a number, is the probability of A plus the probability of B, which is 0.16 plus 0.29, which is 0.45. Again, I could have done that in my head, but you have to communicate. So you guys that are really, really fast thinkers, you have to slow your brain down, and you got to make sure you are communicating. If event C is the event that the person chosen has normal cholesterol, which means we are below 200 milligrams per deciliter, what is the probability of C? Okay, I want you to pause it. And I want you to not just focus on the answer. I want you to focus on the statistical writing, the math, the notation that goes in front of it. Okay, so pause it, see what you got. Probability of C is the how's that? It's the complement of A or B. That's pretty right there. I like that. Which is 1 minus the probability of A or B, which is 1 minus 0.45, which I found here and I showed where it came from, so I don't have to do that again. And that's my 0.55. Now, some of you are probably just about to roll your eyes out of your head because you're like, oh my gosh, I can't believe we have to write all this stuff down. I knew it was 55%. Why do I have to write all this down? You have to write all this down because one of the major concepts of this course is, can you communicate it? Because that's what statisticians do. They don't just crunch the numbers, but they have to be able to present it. That's your presentation. Now, you could probably skip him, but and then you could go to him. If you had this guy, you could go to here and then go to here. Or you could go to here and go to here and go to here. I like all of it. But I would say you would have to have one or the other of those two. But I think you would be okay without having both. But I don't know. College credit's on the line. I don't think I'd risk it. I think I'd write it all out. But if you write it all out and you write something incorrect, you lose points. So be careful. Be confident in your notation. And that's why we practice. And that's why your homework is so important. Okay, two-way tables. Probability and the general addition rule. Who has pierced ears? Students in a college stats class wanted to find out how common it is for young adults to have their ears pierced. They recorded data on two variables, gender and whether the student had a pierced ear, for all 178 people in the class. So I have a total of 178 people in the class, male and female. There we go. There's my data. Totals, the marginal distribution is in bold. So I've got gender and then whether or not you have pierced ears. Suppose we choose a student from the class at random. Find the probability that the student has pierced ears, is male and has pierced ears, is male or has pierced ears. All right, good times. Here we go. A. All right, and again, we're not just focused on the answers. I mean, we are, but we are focused on our notation. So, probability pierced ears, and we have not defined any events here, like he's not A or anything. We didn't do that. So I'm just going to write it out. Probability pierced ears. Okay, so I'm going to look at my table. I have 178 people and pierced ears. Yes, looks like I have 103 people who have pierced ears. So 103 favorable outcomes out of 178 total outcomes. You do not have to reduce that. If it's an FRQ, you do not have to reduce it. Multiple choice, you got to do whatever they did. I don't think that reduces anyway. Is male and has pierced ears. Okay, so here we go. Male. Now I want to focus on this word right here. And, because I'm about to do one that has an or. Male and has pierced ears. Okay, male and has pierced ears. Male and pierced ears, 19. So I got 19 favorable outcomes out of the 178 total population. Okay. Now, here's the kicker. This is the fun part. I'm going to come up here. This is the probability that you're male or pierced ears. Okay, so male or pierced ears. Well, I got 90 males. I got 103 pierced ears. Here's the problem. I can't just add those together. I can't say 193 over 178. The problem is that I got 19 people that are both male and have pierced ears. So I got 19 people being counted twice. And they don't get to be counted twice. So here's what we're going to do. This equals probability that you're male plus the probability that you're pierced minus the probability that you're male and pierced. Okay, some of you are sitting here thinking, okay, but if we subtract them out, they're not counted at all. Okay, remember, those 19 people are in the 90, and those 19 people are also in the 103. So all I'm doing is subtracting it out once. So it takes the double whammy out. So probability that you're male, that's 90 out of 178. Probability that you're pierced, 103. Okay, now remember, these 19 people are in both of these, so they're getting counted twice. So now I'm going to take out the male and the pierced, take that out one time. And that gives you 174 over 178. Okay, so now that we've done that problem, here is your general addition rule for two events. If A and B are any two events resulting from some chance process, then the probability of A or B, probability of male or pierced ears, is the probability of A plus the probability of B minus the probability of A and B. Again, because there's overlappage. So you have to subtract that out. Okay, pause for just a second. What if events A and event B are mutually exclusive? If event A and B are mutually exclusive, which it was not for the males and the piercings, because there were 19 of them that had both. But if it was mutually exclusive, events A and B were mutually exclusive, then this would be a 0. So if mutually exclusive, the probability of A or B is just the probability of A plus the probability of B, because that piece doesn't exist. If they're not mutually exclusive, then you have overlappage, and you have to subtract it out. If they're not mutually exclusive, you don't have the overlappage, you don't have to subtract it out. All right, check your understanding. A standard deck of playing cards consists of 52 cards in 4 suits: clubs, diamonds, hearts, and spades. Each suit has 13 cards with denominations ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. The jack, queen, and king are referred to as face cards. Let's define event F as getting a face card, event H as getting a heart. Okay, so first of all, let's make sure everybody is familiar with a deck of cards. So you have 4 suits. You have clubs, diamonds, hearts, and spades. Clubs are the thing that look like a 3-leaf clover. Spades are pointy on the top. You know what a heart is and you know what a diamond is. Clubs and spades are black. Hearts and diamonds are red. There are 13 cards in each suit, and 13 times 4 gives me the 52. Okay, so let's define event F as getting a face card and event H as getting a heart. So what I want to do is I'm going to make a two-way table that displays the sample space. Okay, so here's my table. Now, event F is getting a face card. Well, the outcome for that is either yes or no. Event H is getting a heart, and the outcome for that is a yes or a no. You either do or you don't. I'm going to add on for my totals. Okay, so to make a two-way table, let's see if we can fill in all the spaces. Well, I know I have a total of 52 cards. So if I do the two yeses, those are the face cards that are also hearts. Well, I have a jack, a queen, and a king that is a heart. So there are 3 of them. Okay, now let's do heart. So yes on heart, but not a face card. Okay, that's all of them, ace through 10. So again, remember there were 13 in a suit. 3 of them are face cards. So 10 of them are not. So that's 10. Yes, they are a heart, but no, they are not a face card. So then that total is a 13, which makes sense because there are 13 hearts. Okay, now let's do some no's. Let's do yes, I'm a face card, but no, I'm not a heart. Well, I'll tell you what, let's do this. Let's do yes, I'm a face card. Let's fill this guy in. Let's just find out all the face cards. So there's a jack, queen, king. So there are 3 face cards and there are 4 suits. So I have 12 face cards total. 3 of them are hearts. Therefore, 9 of them are not. How's that? Work smarter, not harder. Okay. Let's fill this guy in. Well, if he's a 52 and he's a 13, then I should just subtract those 2 to get 39, because that's the 13 in the rest of the 3 suits, and the 13 plus 39 gives me the 52. Again, smarter, not harder. Okay, so then what goes here? Well, if that's a 9 and that's a 39, that's a 30. And if that's a 10 and that's a 30, that's a 40. And 12 and 40 is 52, and that, my friends, is your two-way table. Displays my sample space, all possible combinations of the 2 events. That is my sample space, all possible combinations of the 2 events. Okay, awesome. So now, let's do number 2. I want the probability of F and H. Seems like we just had a formula for that up there. That would be the probability of F plus, nope, let's use our two-way table, sorry. Probability of F and H. Okay, so face card and a heart. So two-way tables are super nice because you can avoid some formulas. Love me a two-way table because you can avoid some formulas. So F and H, and you don't know a formula for and yet. You know the or formula. So face card and a heart. There I sit. Face card and a heart. 3 out of 52. C, or 3. Explain why probability of F or H does not equal the probability of F plus H. Okay, so let's talk through this first. Well, I do know a formula for or. That's the probability of F plus the probability of H minus the probability of the overlappage, F and H. Okay, so why does this not work for this? Okay, so if this doesn't equal this, that means this has got to have some value to it, which means F and H are not mutually exclusive. There's your why. The events, face card and heart, are not mutually exclusive. There they are. There are 3 of them that would be in both categories. Yeah. So they're looking for the vocab word mutually exclusive. So explain why probability of F or H does not equal F plus H. Because event F and H are not mutually exclusive. And then if you wanted to, you could show them what the formula should be. Probability of F or H equals probability of F plus the probability of H minus the probability of F and H. All right, awesome. Okay, so moral of this story is we love a two-way table. If you have two different events and you can do a two-way table, have at it. I will tell you on your AP exam, you will have one FRQ that is on probability. The probability of you having a probability question on your AP stats exam is very high. It's not a guarantee, but it's very high. Love, love, love a two-way table. Another way to organize probability is in a Venn diagram. Okay, so we are going to have event A. And event A is going to be in that bubble. So everything in that bubble represents event A. So however big that bubble is represents the probability of event A. So if I had a Venn diagram and I had an itty bitty bubble, the probability of event A is very small. But if I had a great big bubble, probability of event A is very big. Okay, now it wants us to display the complement. So it wants us to display the probability of a complement. Well, the complement is everything that's not in the bubble. So I'm going to shade. There you go. What is shaded represents the complement of event A. Okay, mutually exclusive or disjoint. Okay, well, I have to have two events for this one. And I have to have event A and event B, but they can't have anything in common. So event A and event B's bubbles can't overlap. So here's event A, and here's event B. Here's A, here's event B. So you can see the probability of event A or B is just going to be the probability of A plus the probability of B. Easy peasy, because there's no overlappage, because they are mutually exclusive or disjoint. They don't touch. Okay. Probability of A and B. Okay, so event A has to happen and event B has to happen, and I want to know what's the probability that both of them are happening. So here is event A. Here is event B. The probability, what represents the probability that they're both happening is that piece right there. That's and. Now notice we have this cute little horseshoe symbol looking thing. And then over here it's flipped upside down. So and is this symbol, looks like an N with no backbone, and or looks like a U, okay? This horseshoe looking thing that kind of looks like an N is called intersection. And I think if you look at your Venn diagram, that makes sense because it's the intersection of event A and event B. It's where do they overlap. Think of two roads at an intersection. In the middle of that intersection, those two roads overlap. So and is intersection. So A intersection B. A intersection B. Or is union. So we have event A and we have event B. Or means I want all of event A, or I could have all of event B. Now, you see there is overlappage. And so that's why when you're finding this, you have to find the probability of A plus the probability of B minus the probability of A intersection B, which remember means and, because you have to take this sliver out because it's in there twice. And guys, that sliver is the A and B. That's the part that's not mutually exclusive. the part that overlaps. Okay, might want to pause it, go back, rewatch that again, make sure that sits okay, especially with the mutually exclusive and the ands and the ors. And is intersection and or is union. Statistics for probability is really big on these new symbols we have, this horseshoe looking thing and the U. I don't ever want to hear you say the horseshoe looking thing. I want you to use the word intersection and union. So when I say intersection, I want you to automatically think of that, and union is the U. Okay. All right. So we're going to use a Venn diagram for the pierced ears problem. Okay, so we've got our dudes and our chicks and whether or not they have their ears pierced. Okay, we're going to do a Venn diagram. Instead of a two-way table, which they have here, we're going to do a Venn diagram. When you do a Venn diagram, you have to put the probability inside of it. Okay, so here we go. Now I have two things. I have male and pierced ears. So my two events are not male and female, pierced and not pierced. I'm not going to have 4 bubbles. I'm going to make one bubble be male, so then the not of that would be female. And I'm going to have one bubble be pierced ears, so the not of that bubble is going to be not pierced ears. So here I go. I've got, I'm going to let A be male and B be pierced ears. Okay, so here I go. A, B. Now I drew them overlapping because I have males that have pierced ears. Okay, before we answer the questions, let's put some numbers based on our two-way table. Let's put some numbers in our Venn diagram. Okay, so first of all, let's focus on how many males total we have. I have 90 males. Now I cannot just put 90 right here because I have to take into account this piece. So this piece in here has 19. And again, I can't just put a 19. You can't put numerical values. You have to put probabilities. So 19 out of 178. So that's that middle section. So now I can't put 90 over 178 here because I've already got 19 of them in that middle wedge. So I have to take the middle wedge out. So 90 minus 19 would be 71. So this 71, let me see if I can do some coloring. The 71 out of 178 isn't the males. The male is the whole bubble of A. And to get that value, guys, look at it. It would be the 71 over 178 plus the 19 over 178. And that would give me my 90. So you guys see that the 90 does not sit in plain sight in my Venn diagram because A's bubble has a piece of it carved out. So when I write the big 71 over 178, I have to take the 90 and take that piece that gets carved out of it. Because if I had the 90 where the 71 is, then I would have the 90 over 178 plus the 19 over 178. Now I got 19 males being counted twice. And I can't have that. It's very logical. Very logical. Okay, now event B is pierced ears. Okay, but there is a wedge of bubble B that's already been accounted for. 19 of my pierced ears are already in that bubble. So let's find all my pierced ears. Pierced ears, yes, I got 103. So I have 103 total pierced ears, but I got 19 of them already in that center wedge. So what's going to be left over here is the 84 over 178. So guys, the 84 over 178 represents my females that are pierced. My yellow, let's color that. He's going to be green. Green for the girls. And again, this is not the girl bubble per se. This is the pierced, B is the pierced bubble. The green part of the bubble are the girls that have pierced ears. Again, that middle wedge, that 19 over 178, are the males that have pierced ears. So that 19 gets counted with the 71 to make the 90, and it gets counted with the 84 to make the 103. Stop for a second, chew on that. Make sure you understand, okay? And if you don't, star it and ask about it tomorrow in class. Okay, so now we've done all the yeses. So now let's do all the nots, all the space outside. Okay, so the space outside these bubbles means I am not male and I do not have pierced ears. Because if I'm male, I'm in the yellow. I need to color the center wedge. Hold on. All right, here we go. If I'm male, I am yellow or blue. If I am pierced ears, I am green or blue. So I've got some females in the green. I've got all my pierced are in the B bubble. All my males are in the yellow bubble. So the only number that's left who is an outcast, who is an outsider of being male and being pierced, are those 4 people right there. And they live out here. They live in the box outside the bubbles. They take up all that space. 4 out of 178. So there's your Venn diagram. So that would be part A of an FRQ. Okay. Now that we have all this information in a Venn diagram, I can answer these questions. Okay, male and pierced ears. Okay, well, let's work on our statistical notation. So male, I've defined it, I just erased it, but I had defined event A as being male and intersection, sorry, pierced ears. So A intersection B. Well, intersection is where things overlap, and that's the blue part. 19 over 178. Okay, male and no pierced ears. So now look, because you're going to have to write this part that's in black right here. Male and intersection, the complement of pierced ears, not pierced ears. So I'm finding the probability of this. So the probability of male, that's yellow, and not pierced ears, male, and not pierced ears. Really easy to see in the chart, and it's right. I don't want to draw on my drawing. It's the yellow part. I'm male, but I do not have my ears pierced. Remember, green and blue is pierced. So I am not green or blue, but I am male. So I'm in the A bubble, but I'm not the 19 over 178 because 19 of us have our ears pierced. So 71 over 178. Okay, female. Well, we defined event A as being male. So female is the complement of being male. So a complement and intersection, pierced ears. So I want to be female. Okay, I don't have a bubble for female, but I know that I am not male. Okay, if I'm not male, again, I hate to draw on my drawing. If I'm not male, I'm them. Oh, dang it. All right, hold on. I think I can undo it. Yeah. If I'm not male, I'm them and them. Those are all my not males. Because think about it, what's 84 plus 4? That's 88. And then look back up at your table. I got 88 females. So not males have to be outside of the A bubble. And that's the 84 and the 4. Okay, so those are my females. But I want the females and I have pierced ears. Well, the 4 over 178 just lost out because now I want to be pierced, which means I have to be inside the green bubble. So that's the 84 over 178. I cannot include the 19 because they are male and I am not. I am female. All right, female and no pierced. Now remember, I circled these two. These two are both your female because we are outside the A bubble. And intersection, not pierced. So B complement. Well, that's those guys. You have a quiz. I can't remember what it is, but I'm sure I'll communicate it with you. And there is one that has a Venn diagram on it. And the results are normally not awesome. And here's why. People forget. The main reason people forget, because you're going to practice this, like you'll get the hang of it if you haven't already. But people will look at this, and instead of putting 71 over 178, they'll just put 71. Well, that's not a valid probability. That's bigger than 1. So make sure you write your probabilities as fractions. The other thing people will do is they'll look at this big A bubble, and they'll go 90 over 178. But that 90 actually never gets written down on here because the 90 is split into a 71 and a 19, and that makes up the whole bubble that is 90. But this number out here only represents the part that is yellow, and this number out here only represents the part that is green. So make sure you have a really, really solid understanding of that. Okay, so I hereby take our old formula where we had ors and ands, and I now replace them with unions and intersections. So probability of A or B, it's probability of A union B, equals the probability of A plus the probability of B minus the probability of A and B, which is now the probability of A intersection B. And then I think that bottom formula right there is on your formula sheet, but we'll look in class. Okay, last problem. Who reads the paper? In an apartment complex, 40% of the residents read USA Today, 25% you read the New York Times, 5% of the residents read both. I can already see a two-way table or a Venn diagram, one or the other. Suppose we select a resident of the apartment at random and record which of the two papers the person reads. Part A, make a two-way table that displays the sample space of this chance process, and then B, construct a Venn diagram. Okay, I want you to pause it. And I want you to make a two-way table. I'll get you started. You have two events. Event 1 is USA Today. Yes or no? Event 2, New York Times. Yes or no? Make a two-way table. Make sure you leave room for your totals in the margins, and then make a Venn diagram. Okay, so pause it. All right. USA Today, if I can spell. can't, apparently. Yes. No. New York Times? Is that right? Yeah. New York Times. Yes. No. And totals. Let's see. These are all percent, so I don't have actual people, so I know that my percents should equal 100%. I'm going to keep it in terms of decimals. Okay, it says, in an apartment complex, 40% of the residents read USA Today. So USA Today, yes, 40% total. Now that 40% is going to get broken up into the New York Times yeses and nos. But 40% total read USA Today, which means 60% do not. Okay, then it says only 25% you read the New York Times. So New York Times, yes, all the way over. 25%. Okay, well now I know he is 75%. It's like a Sudoku almost. Like as you can fill stuff in, fill it in. Okay, that gives me one more nugget of information because right now I'm stuck. I can't do anything else. It says 5%, that's 0.05, read both. Boom. Now I can finish the whole thing. That's 5%. This is 35%. If that's 5%, that's 20%. That's 20%, that's 60%, that's 40%. 35 and 40 is 75. Ta-da! I love a two-way table. Love, 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 love. Okay, now it says make a Venn diagram. Okay. I'm going to let event A be USA Today, and event B be the New York Times. And I do have people that read both, so the bubbles overlap. Okay. If this value right here was a 0, then those bubbles would not overlap because nobody does both. Okay, let's see. Speaking of the overlappage, that's 0.05. Now I can put a plain 0.05 in here because that's already a percent. In the last Venn diagram, we wrote them as a fraction. It's totally fine because that was part over whole. This one's already done the part over whole and converted it to a percent. So 0.05. All right. I need to label my bubbles. He's A, he's B. Okay, so A is USA Today. So the first bubble is USA Today. Here's where people screw this up. USA Today, the total number of people is 0.40, but I can't go in here and put 0.40 because the number that's out here only represents the part that's outside the overlappage. So if it's a 40% total and the overlappage is 5%, and that's your 35% because now the 35 and the 0.05 together make the whole bubble, which is 40%. Okay, let's do event B is the New York Times, and that's a total of 25%. 5% is in the overlappage, so that's a 20%. Now I just need my number that's out here in no man's land. These are the people who don't read either. That's 40%. Now, super paranoid people, all you have to do is take every percent that you see in your Venn diagram, and it has to add to 1. If it doesn't, you have screwed up. If it adds to 1, odds are the probability is that you got it right. So 35 and 5 is 40, 40 and 20 is 60, and 60 and the 40 is 100. There's my Venn diagram. All right, part C. Find the probability that the person reads at least one of the papers. Okay, so if I want the probability of at least one of the papers, okay, well that to me, is the complement of reading none. If I read at least one, that means I could read one, I could read the other, or I could read both. Instead of doing it that way, I'm just going to find the probability that I don't read any. Well, okay, hold on. It's the complement that I don't read any. So the complement means that's 1 minus the probability that I read something. So, well, that would still have to add them all together. So maybe not. Oh, no. Let's do it this way. Probability of none complement would be 1 minus the probability of none. Yes, I was right. It's 1 minus the probability of none. If I read something, then that is the not of none. I'm going to say that again. Wrap your brain around this. The probability that I read something, that's the at least one, is the not of none. It's 1 minus the probability of none. That's what the not means. So these two things right here say the exact same thing. The none complement is 1 minus the probability of none. Well, that's easy. The probability of none is 0.4. So the probability that I read at least one is 0.6. Now, if you wanted to do it the hard way, not that it's hard, you could, that, and that, and add them up. But you have to show me what you're adding. You'd have to say the probability that I read both plus the probability that I read the USA Today and not the New York Times plus the probability that I read the New York Times and not the USA Today. And then show me all three values and that you're adding them together, and that gives you 60%. I'm telling you, the complement is the way to go. Find the probability that the person doesn't read either paper. Well, I just did that. So I used that. Probability of none is 0.4. Those guys. Now, guys, very rarely are you going to have a two-way table and a Venn diagram in the same problem. Usually you have one or the other. It's just a way to organize information. Me personally, I am team two-way table. But I don't mind a good Venn diagram. And, don't be so one or the other, because multiple choice could give you one or the other, and you need to be able to work from both of them. FRQ could ask you specifically to draw a two-way table or a Venn diagram specifically for one or the other. So you need to be comfortable with that. Okay, last things before your brains explode. AP exam tip. Many probability problems involve simple computations that you can do on your calculator or in your head. It may be tempting to just write down your final answer without showing the supporting work. Don't do it. A naked answer, even if it's correct, will usually earn you no credit on an FRQ. You can't have naked math. They want to see that you can talk the stats lingo, that you can communicate like a statistician. So when you do your homework, really, really, really practice and focus on that part.